which means that you already know the regularity for a reference equation is known. And you're transferring the regularity to other equations. So in the interest of explaining the arguments more clearly, I will only be focusing on the Laplace operator with the right-hand side. Okay? And even in this case, it's not entirely obvious what happens. Yeah, so normally what happens is, instead of this operator, if you take something like, let's say, Aij, Uij, then you need smallness of Aij to the Laplace, some norm. And similarly, you have smallness here, which you will see. And when I say transfer regularity, what I mean is, I have this equation, I want to have some regularity for this. I will transfer regularity. So I know some regularity, for example, for the harmonic functions, right? So I want to transfer the regularity from here to here. Okay, so that is the basic way. And now let's go to this. For WTP estimates are as follows. So if you have, so for notation, E will be a ball. And if I write something like ER, it's ball of radius R. And grad U will be the gradient of U. And like grad square U, this will be the ratio. So the starting point is one. If I have this, let's say 2 weights, okay, then I have the following V1, V2U. This means the constant does not depend on U. So FLP. Okay, so this is what is called a random index. Why is it called W2P? Well, this is W2P, right? And this was first done, of course, by Calderon-Zgymund. And how it happened in this for the Laplace is you have the Green's function, right? So you convolve, and then you get a kernel which has homogeneity minus n and has the right cancellation properties. So using singular integrals, you get this estimate. The approach I'll outline today is a more PDE approach. So no singular integrals, right? And of course, so we will look at p bigger than 2, p less than 2. Okay. So I want to, okay, so before that, let me just mention some, I don't know if I explain it. So let me just say something. So the 2, for p is equal to 2, okay, this is not very hard. This is there, for example, in Evans, okay. This is essentially H2 regularity, and you take difference quotients and okay. What we have is we have one endpoint, which is, let's say this is W2. We have p is equal to 2, and I said we want to transfer regularity. So at the other endpoint, we have something like W2 infinity, which means that the second gradient, this is sort of bounded, which is like C11, right? And we want the range of p here, so it's like an interpolation that's happening. Okay, so we are going to assume this estimate, which, like I said, is in Evans, and this is where this is for harmonic functions. And then we will show it for all p bigger than 2. W2 is what's happening. Okay. All right. So we are looking at LP estimates. Now, what is the information carried by an LP function? So, as you know, if I have something like this, right, I can write this as a constant like p, 0 to infinity, 1. Measure d down there, right? So really the information that if I want to study the LP norms or something, I need to look at the decay of the level set, right? So I need to get some decay of the level set. And how we will do this is there will be a step 1 decay, scale 1 decay, scale 1. And then, because you have a PDE, so this is where the PDE comes, you have certain scaling properties of the PDE. So then you get decay at all scales. And then once you have decay at all scales, you will get this LP now. Alright, so this is how it goes. So what do I mean by decay at scale 1? So let us say, let's forget about all of this. Let us say that I have some function u, right? And I want to prove the decay. I want to look at the decay set of this. Let us say I show that for some epsilon, I have something like this. Okay. Let us say I get a decay like this. Then, because there's a scaling unit that goes on there, you can scale this to lambda naught less than, and this should be measured until the unit style. Then equal to epsilon. Here it will be greater than. So this would be step 1, and this would be an iteration. Now, if you keep iterating this, you get powers of epsilon here, okay, which will sum. We will do this later in greater detail, but this is the idea. So this is what I mean by saying that we have decay at scale 1, which is we have decay at scale 1, and then we do it at all scales. We do it at all scales. Like what I can type, this is lambda, so I can put lambda equal to lambda naught square, and so on, and get decay. Okay. So this is how it goes. Now, ideally, then following this, we would want to look at this quantity, right? We want to look at this quantity, but we can't look at this. The reason is because we are looking at LP functions, and pointwise, it's not really a scale invariant quantity. Okay, so I have a function, the LP value at x naught. So let's say I have this. This is not really this is not the correct thing to look at, because by changing the scale, so if I have this, let's say it's an x naught and this is the ball, I could have something while happening here, and this will change this norm, right? So I don't have control. On the other hand, as r becomes really small, as you know, this is finite, this is anyway going to go to 0. So I don't really have control, right? So to make it scale invariant, I take the average, and to make sure that I do it at all scales, I look at this. And this, as you know, is the maximum function of f, right? Is okay? So then the correct thing to look at here is not something like this, it's about the FT functions, but to look at something to do estimates like this. So, and instead of making it square, make it square, because it's make it feel like is to study level sets of this kind. Okay, it's clear, right? Why we don't do function, we do maximum function. Okay, and yeah, so everybody's okay with maximum functions, right? I don't need to say. Okay. Okay, so what will happen is, let's say f was 0, right? If f was 0, then this is essentially harmonic. So then if I had pointwise control at some point, since I'm looking at this, right? If I had pointwise control at some point, then by linear regularity for harmonic function, I have control everywhere, right? Which means that this level set for large enough lambda anyway becomes empty. So I mean, there's nothing much to do here. Okay. So then the game is on this thing to make this small. Okay. So if f is small, then we want to say it's close to harmonic function. So what is it? Formally, what happens is, let us say I magnify u. Okay. I magnify u by scale lambda. Okay. Then what does the equation become? It's Laplace u lambda is lambda square f lambda x. Let's call this f lambda x, right? Which means, ignoring the certain properties here, as this lambda goes to 0, which is as I keep zooming in, this is becoming smaller and smaller. So I'm getting closer and closer to a harmonic function. Okay. So what would happen is, conditional on the fact that f is small, I can always do some approximations. And making f small is not a big deal. Why? Because I can always multiply by a constant and make it smaller, right? Because then the estimate only a constant will then come out. They'll be divided by. Right? So that is the domain is bounded. Yes, sir. Domain is always bounded. So there's no unbounded domain going on. Domain is always bounded.
Interior estimates.
Those are interior estimates. Yeah. So this is B, and this is B2, and this is B2. So those are iterations, those are nets. Yeah. So the P is equal to it's a nets. We are doing P. So the idea is clear, right? Why we expect to get closer and closer to a harmonic function because of the scaling. Okay. So what ends up happening though is that
is there any problem for P equal to 2 case?
So P equal to 2 is already known, right? That's what I said. It's in average. I'll give you the exact reference later. It's in average. P is equal to 2. This is the interior H2 regularity. I'll use the boundary version of this also later. But this is not very hard because you just do it, you do a finite difference and you can get it. And yeah, but we want to do it for P. So for P, the first time it was done using singular integrals, right? We are trying to do a PD proof. All right. I mean, there's still harmonic analysis. Yeah. So I was saying that we want things like that. So now, like I said, the smallness of F, right? So when we are doing it with grad school, maybe you have some smallness of F condition here. So modulo the smallness of F, we get something, right? And this is replaced with the maximum function. So I will skip some of the things. What ends up happening is to get something like that, you get a covering. Okay, you get a covering which is almost optimal. So you want an exact epsilon there, but you get greater than or equal to epsilon. So you want a covering argument which lets you use, which lets you not cover it exactly epsilon, but greater than or equal to epsilon. And that is a variant of Vitali covering. Okay, so I'm going to first state that. So that would be Vitali covering. So I'm sure you know this. Right? CB collection of balls with positive radius in RF with bounded radius. So if you can't take unbounded radius as 0 because you can just take balls around the origin and that's a bounded, right? Bounded radius. Right. Then it exists a finite it can be either collection DI in the collection such that 5 times BI is covered. Okay, so C right? So this is the uncountable version of Vitali, right? So if you have countable, this is just 3 or finite, right? Okay, so it's there in everything added. Okay, so this I'm going to presume, and I'm going to do a modified version of this. So let's start this demo. You choose a density node, and let's say B covers C in B, and C small in B, okay, such that B covers C density. This is what you saw yesterday in Arvin's lecture. So I'm going to use the Vitali version. You can also do it using the Calderon-Zgymund version. And the difference is, since I'm going to work with balls, Vitali is for balls, Calderon-Zgymund is for cubes. Okay. So that covers C density, which means what? Which means that for all x in your ball, if C intersection B are x, then B are x intersection B1 contained in B. So whatever ball covers C in density will go and sit inside D, right? Then the conclusion is, so I will rotate the other way. Measure of E is like 1 by 20 power the dimension epsilon B. So this is the modified Vitali, the P of the views. So what ideally we would want is something like B is equal to epsilon C and things like that, but we don't have this. But this is good enough. So the proof is not very hard. So this condition, I have this, right? So we get that for almost every, this is basically the right points of the characteristic function. For almost every x and c, there exists a radii. It's like, I mean, these constants 2, 3, 4 don't matter, right? Or x less than 2, such that intersection drx x is exactly x1, right? This is okay. This is okay. But it's O. This is 0. Sorry. This is 0. This is 20 power. Is this okay? If it's not, then you take the characteristic function of C. Okay, take this average. This is a continuous function of R, right? And then the Lebesgue points of this will give you this, right? So, okay. So I have this, and that is like the biggest radii where that happens. And C intersection dr x is falls below the density for all R over Rx. That this is like the last time it happens, and after that it follows continues. You take like a super. Okay, so then now I have a covering of C, right? By trivially, right? So by number 1, there exists, I can get the points with such that B, Ri, Xi are disjoint, and I can cover C by 5 times this. Right. So 5 I'll just put in the radius. B5. It's okay. I'm just applying to that. And you see, you need 5 here, right? Because there is a compact list, something that can draw this to the complex. Okay. This one and this. So the choice of BRK, right, implies that you have C intersection B 5 RK XK is because this is greater than the RK now, right? So the density falls. So D 5 RK and X and OK. This I power N epsilon N. So I'll start losing constants at some point. So here I've not lost, but okay. XK. And that I believe is 5 for N, 5 for N, E intersection B R K, right? This is because RK at RK the density is exactly epsilon. So I'm just writing the whole thing again. This has to be okay. Now, because I took a constant RK2, right? It doesn't matter. The RKXK is at most like 4 power n to there. So if you remove the constants, approximately RKXK E1, right? Because XK, as you know, is in E1. RK is like at most 2. Like 1 or 2. And I'll just put 4. You understand it's an overestimate. It's like 3 at most, ball 1. So I'll just put 4. So now I just measure C, right? C is I have a disjoint correction. 5 RK XK intersection C. That is times this, and that by that is calculation there. Is 5 power n times P epsilon with the P RK XP V1. Now this is disjoint, right? By the choice, and I'm going to use that now. This is like 5 times 4 is 20 or n epsilon, and this is disjoint, so it just comes up most in D. So that finishes the modified Vitali, right? So that is that. I'm going to state one more result which I will need. Since I've used this already. So, like I said, so the one I mentioned in the beginning was the interior H2 regularity. Now I'm going to use the interior H1 regularity. Okay, so this is again in Evans. All my references to Evans are like the chapter, I think 6. Chapter 6, the section regularity about this. So if Laplace U is there, this one is boundary, this is not interior. So I need this D1. Then D1 D2 square is absolute constant. F square. So in Evans, you will see that it's not just F square, there's also a term in U. But because I have this very special operator, this is unique. By standard argument, the U goes away. Okay, so you just have boundary. So I'll just say this. Now we'll come to the main part. Now, I said in the beginning that modulo the right hand side, I almost have a harmonic function, right? This is like the version of that. So I'll prove this in the end. You will see how it's implied for P1. There exists a principle. This is that level lambda thing that I had written earlier. So that any prescribed any smallness, there exists a delta such that you solve plus q is equal to f in some domain which contains, let's say, 100 balls. So instead of doing all this, simplicity, you can just write some really big ball here. Okay? Doesn't matter with all the cases. Now, what the hypothesis is saying is, if I have a solution, right, such that I have smallness in n, okay, and I have control at some point. I have control at some point in the ball. Let's say I'll take E1, which is non-empty. If I at some point in the ball, if I have smallness in f and I have control on the curvature here, right, then it can't rise above this by too much in too larger part of the ball. E2u square greater than n1 square section B1. That most epsilon times E1. It's the content here, what we are saying. If I have at some point in the ball, so I have a ball, at some point in the ball, if I have a function over here. I have a function. If I have control at that point, right? This point was I have and my right hand side is not too large, then it can't cross this. It can't become like 2. So if I narrow it, it can't do this in too large a set. Okay. Not but at least analytically it's clear, right? Statement is clear. So let us say I prove this. Let us say I have this. Okay. Let us say this is true. If this is true, then now I'm going to remember. Anyway, so let us say this is true. Assume for now. And I hope I've convinced you in the beginning why this is reasonable. The right hand side is small, is almost like harmonic function. Right? So, for example, if f was 0, right, then a pointwise control here by iteration already gives you control everywhere. So this n1 for large enough n1, right, is anyway empty. So this is 0. This is trivially true. Right. So all I'm saying is I can do the same if my right hand side is small enough, which I said, like I said, is not a problem because I can multiply by constant. So this already therefore gives you the full thing. So now this is step 1 regularity. I said now we'll just iterate and get it done. Let us look at so as a corollary, this is more like a corollary, right? So let us look at it in the other direction. If you solve plus u is equal to f in again that really big ball, and let us use that. And if my density is like large, so if x such that square is larger than n1 square is large, be large. Epsilon is not. This B now is not, can be any ball. Then this, because of this will go and get contained there, right? So you just decide the statement. E is then contained it. Square larger than 1. And f square. Like, is this okay? This is your corollary. So I'm saying that if I had some point where it was small, then my density must be small. So if my density is large, that means there's some point on which either this is larger, this is larger. So this is just a corollary. And so this looks like now the covering thing, right? I'm saying that if I have some covering density, it goes and gets contained there. This is like now we are in the setting of the Vitali, right? That's what we will do next. Everyone's okay that we are now in the settling of the Vitali, right? Almost there, right? So now we just need to get the sets appropriately. So now let's what is this like? 4, 5, 6. Right? So suppose that the beginning of the sets square, if the density is small. Remember, this is not a restrictive assumption. Why? Because we're multiplying u with the suitable constant, I write the constant later. You can always ensure this. Alright? So this is not this hypothesis is for free. Okay. So suppose that I have this, then or epsilon 1 is the Vitali wala number. E power n epsilon, and any like scale that you start using in number 1, we have first part measure such that n square less than or equal to 4 times that square and x equal to 1 plus this factor and the other factor is plus 1 as factor. So why is this true? What is this? So the small, this is your C, right? And this whole union is a D. And apply Vitali, the modified Vitali, right? So you get this. This epsilon. I should have epsilon 1 there. So I've just renamed that constant as epsilon 1. So this is Vitali, right? You're okay now. You take C to be this, D to be this, the union. So now what we will do is we will iterate this. Okay, so before I do that, the scaling thing that I was mentioning was what? So let us say I have some scale. I want to look at level sets which goes in scale lambda square, and so on. Okay, something like that. And so if I look at Laplace of, right, this is just. I mean, this looks very clear. Because we have Laplace, right? We have this, right? So now, since I have this equation, I apply whatever I've done with this. Okay. So then what do I get? I get x in v1 such that the square. This values 1 times 1. So this was 1. This is using square. And Okay, I'm just applying whatever I've done now to this. Now let us go to the final step. In the final step, now I just iterate this, right? So now I put step 3. I'm just going to now set lambda is n1 square. Okay, like I iterate the whole thing. So what do I get? I don't get x and g1 again. N e square u square larger than n1 square, so that is the to the power k, right? Less than or equal to epsilon 1 power k m square larger than 1. So this is because I mean there is no k dependence here, so I just do this on an epsilon 1 k side multiplied at every stage. So the kth stage you have k here, right? And the other ones because it keeps coming up in the f's. So summation I is 1 up to k epsilon 1 power k square is larger than delta square and n1 square to the power k minus I, right? So you just iterate this estimate here. So I step, let's say I put the next step, then this goes and gets replaced here, right? Which is why I get an epsilon 1 square here, and then that plus corresponding term. Those two get added up with this gets added up with power epsilon 1. The previous one gets added with epsilon square, so you get k minus I, right? That is this k minus I, and this keeps track of what stage you are in, right? Okay, so now we are done. Yeah. So up to here it's clear, right? I wrote that, but I'm having used this. So recall that characterization I wrote for LP functions at the beginning, right? I said that the LP functions are norm is up to some constant, some weight times f bigger than lambda, right? And I've got the decay. I'm now just going to use it and sum it up. So the hypothesis had this smallness condition, right? And I said it's free. That is because, so now let me take this theorem and theorem is Laplace u. Then P, I'm just rewriting what I written in the beginning. Is up to a constant. Maybe B100 plus this U is necessary, right? Because we are not doing it, we don't have boundary values and all. The E estimate, B1 to B100. This is what we do. Now, without loss of generality, I think if you use U tilde is some alpha naught U. Alpha naught is some constant depending on the dimension epsilon by, I think if you take U2 square plus FL2 square, something like this. Then by doing this, rewriting the equation, you can always assume that set where, so if I do this, then this is just a constant. So the derivative of this pull up, nothing will happen, right? V2U square bigger than n1 square. I can always assume that this epsilon times. Okay. And again, similarly, I can always say something like like apples delta. Okay. So this delta we will. This is the delta we will again. So again, so maybe this for delta we put like 1 by delta. Right? Okay. I can always ensure this now, right? So when I divide this is just a number. Laplace U will be Laplace f by this, so E into. So anyway, by rescaling, I will assume this. And we'll remove all this. So what will happen is ultimately we will get a bound like e to u power p is at most a constant, right? But because I have this factor here, right? So let us say with this scaling, I prove that. Let's stop for now. E to u tilde power p, right? Let's say I show this is a constant at most. Then this is like alpha naught power p. Should be alpha naught power p. E to u tilde power p is 1 by is like 1, and this is 1 by alpha naught power p, right? Which is, if I start ignoring constants, which is u square plus f square power p by 2, right? Right? Then up to a measure by Jensen, this is u power p, f power p, right? You just use Jensen. P is bigger than 2, right? Remember, so p by 2 is bigger than 1, so I can use Jensen here. So therefore, it all boils down to, after all these feelings, I just need to prove this bound. Okay, you agree? Then I'll get that bound by this thing I mentioned. All right. Yeah, that's not complication. So let us compute. I'm looking at d2u power p, right? In what? What is this? Up to a constant. All that. Now I'm going to replace this with the maximum function. The maximum function thing. U square p by 2. Okay, I'll do this. P by 2. This is the maximum function, and then again the constant is p 1 0 to infinity. Now the power p minus 1. The distribution function of this, right? So x and let's say w p minus x. And p square. Right? Now this. Now I start using the iterated result there. Is p. So what I'll do is I'll take 0 to 1 and 1 to infinity. 0 to 1, I'm going to bound this by like measure of the ball, right? I'm going to finite step. Yeah. Plus. Now I'll just break this up. So this is 2. This is like p by 2. This is like n1. I'll count this later. Larger than. Right. Okay. And then, where was it? So now this thing is here, right? So I'll write that. We just write that. E on plus this will our I from 1 to k. Epsilon 1 power I m square greater than delta square n1 to the power k minus I plus summation from t0 to 1 power k u square u, right? Now this is again measure of the ball, okay, because it's in the ball, so it's like at most. So I have this sum which is like n1 power kp epsilon 1 power k. So if I choose something like n1 epsilon 1 less than 1, this will converge. Is it okay? This is bounded. Now let us come to this. This is bounded. This is okay. over here, the worst case scenario here is you start from 1 and go to infinity, right? Because again, I pull out this epsilon 1 again by the same thing, this convergence. So I only look at convergence here. That is just the epsilon.
So the second inequality shouldn't be P by
Which one?
the second inequality in the subboard, because you have P by 2.
Yeah, P by 2.
Yes. So in the next step, then shouldn't be P by 2. Will the K clearly?
No. So this is P, this is 2. So I'm going, this scale is P by 2, right? So I don't know. So you can do it like this. So if you have so if you take something like I don't know about KP greater than about K, okay, I take this sum. This will always like up to some constant, always lower bound the norm of x. Now P by 2. So P by 2 times there's a 2, so that makes it. That's one.
And the previous one, this one also, it should be P by 2.
Yeah. By 2. But okay, so modulo all this is okay because this is P over 2, that takes the 2 and makes it P. Okay. I just which is from here. This is scale P by 1. P by 2. Okay. So yeah, I'm going to find this right here. Right? 15 minutes to do this. Now, actually, I'll not say. So this summation here with Fi and the correct lambda epsilon I, this is exact. I mean, it's exactly the identity I've written here, and that becomes the LP norm of it, which again I said was sec delta. Right? It's 1. So the whole thing is a constant. Okay, so then that thing counts. Okay. Yeah. So now we are left to prove this thing, and this is so you agree that this is the most. This is the one that's left. Okay, so we'll prove that. So you see, once you have that lemma, the rest is just rescaling and properties. Right? Now, because the set is non-empty, right? In a 4 ball, at least, always do. So let me just write the whole thing. I have this, and similarly for F, right? At least there is some radii for all this implies because I have large enough balls in B4, B2 square, it's like at most 4 power n, right? have 2 power n, 4 power n. Right? And similarly, since the maximum function of f is also at most delta square, larger response, I get now now Poincaré is okay, right? I'll use Poincaré. So du minus du, this is the average in, let's say, B4. Notation means the average of du is B4. Okay, by Poincaré this, I should write a 4 square. So actually, Poincaré, what happens is this R, this will be R. So this has to be the scaling factor because on the right side I get the gradient. Gradient scale pulls out a factor of radius, so you need to scale by that with the correct scaling, right? So this is and the average is d2u whole square, right? d2u whole square I bounded. So this is some constant. Okay, so I can also remove this. Right? So now I said we will now approximate the harmonic function. This is the main part, which is I look at harmonic function and I want to do a replacement for v, right? So I look at u. Yeah, minus I'll subtract off a plane. Solution is okay, right? dui the gradient is a vector, so the average is like a vector. So 1. So this is the harmonic replacement. Now I have this. Then this is so this let's call I don't know f. Right. This is again another legitimate function which has the same boundary values as u, right? So you know that harmonic functions minimize the energy, right? Right. So therefore, this implies that in B4, this is a smaller one. So that e square is less than or equal to what is the gradient of this? Gradient of u minus the gradient of this is this goes away, right? You just left with the average. That is gradient u minus gradient u average square, which is 1. So also is this okay? Gradient u, this is a linear function, so I just get the direction, and that square I bounded it, so I get this. Right? If you don't like to use minimality, you can also just take this u minus this as a test function and do the unit energy estimate. You get the same thing, right? Okay. So now this is the so I have used. So remember I said that I have W2 and I have C11 here. I'm going to use this now for V. I'm going to use C11 estimates for V because V is harmonic, right? So since V is harmonic, we get in by integral C1 S is G2U square, let's say infinity in V3. Oh, sorry, V3. I can find a constant so that this happens, right? And so you look at this plane. V minus this, you take this as a plane. Okay, you look at this plane, and the second derivative of this plane is 0, right? And u minus v minus this plane is 0, right? And this also some boundary value problem. So just saves also this. So then you use this estimates. Okay, the interior estimate. Because like I said, you subtract off the boundary value is 0, Laplace is there because this is the plane. And then you do that and you get v3 minus v squared. Less than or is up to a constant. Right hand side will be f. Right, I'm using this now. Is again, I've started with some assumption there. Delta squared. Right. Now you use the weak 1 estimate. You know, right? Weak 1 the maximum functions. So you get lambda m squared. Sorry. V2 minus V square greater than lambda, right? Is up to a constant. D2U V whole square. This, right? So it is again delta square. Okay, weak 1 1. This weak 1 1. This.
You V to be equal to that in the for one the whole before ball.
This is V Laplace V is 0 and V4 on the boundary V is this.
Then how are you computing gradient of V as the same function on the
Which
whole?
gradient? Which gradient?
There you
This step.
there you said like you put.
So here what I said was you take
But it's not the boundary then.
no. Okay, so if you you take this function is defined everywhere, right? It's not just defined in the boundary. So it is a function with the same boundary values as V.
So if I use
And V is a harmonic function. Harmonic function minimizes the energy. So you have this. The gradient of this is exactly this, and that is bounded. If you don't want to use minimality, you can just do the energy estimate. You take this as a U minus this as a S function, put it here, and use your energy estimate. I mean, you can do it either way. Okay, so this is okay, right? Weak 1 1 bounded by this bounded by this comes here, right? So yeah, so now claim is that the set where actually contains in this set, which is small. I should probably like to describe this is in V1. This is in V, X in V1. Such that. So when I write this V3 here, I'm multiplying by the cancel function of V3 and all that. V minus V square larger than N0. Okay. Where N1 where is like max of N0 square, constants, right? I'm using 4, right? So 4 N0 square and 2 power N. Again, these constants. But you see, this has nothing to do with you. So for this, right? And how that happens is, well, I'll start here and show if it's not clear. So you start with, let's select a point in this set. So I'm doing it like this, not square, right? Then, so if R is below 2, then you know that VRX is V3, right? Because this is in V1, this is 2, 1 plus 2, at most you have done radius 3. This is in V3, which is why I took V3. So it depends on this, you change this. And you know that sup R square is less than or equal to this, this square plus 2n. So you get something like 4n non square. Now how we got this was break this up. This is okay, right? Because I'm in small radius. Okay. So now I mean, I probably just mentioned. So what I've done here is I've said that E2U square y in D3 okay, is less than or equal to 2 times V2U x V2U. So all of these are matrices. You treat this as like an Rn square and take the Rn square norms. Okay. This is what I've used. And to get this, you just, I don't know, you expand something like x minus 2y whole square bigger than equal to 0. You get this. Okay. And if R is bigger than 2, anyway, I have the bound on 2 power n, right? Okay. So that's it. So then that says that this is less than n1 square. So there's a constant 2 power n that comes for R bigger than 2, I will get 2 power n. Okay, same set of calculations, but here it's easier. So I have 4n0 square, 2 power n. So if n1 is max of that, then less than equal to this is here, which is greater than equal to this in there. and that finishes the plane. That finishes the plane. And finally, now I can erase this. Finally, I have m square. Less than or equal to, since it's now contained, it's the d2 u minus d square larger than n naught square at 4 thing, right? And that I've already estimated here for you. Sorry. Okay. Again, by the same set of things by I'm reading the calculation. N naught square. Again, this is like delta square. This is delta square, and now delta square by which is less than c delta square because n naught is bigger than 1. And now you choose, I said, where the dependence. This is how you choose the delta. Given in epsilon there's a delta, you just choose it like this. So this finishes. So yeah, that's the end of it. I don't have more.